Assalamu alaikum, sir.
Wassalam Irfan.
Sir, already recording start कर चलिए.
Uh, that's okay. Actually, it's by default started. I mean, when I created, this link, and now I understand you will be in trouble. I mean, when you run it from YouTube, first 20 minutes will be nothing because I started at 4.
But you can pause it, sir, to
Why
save
should
space.
I? Okay. So we can start now, I think. I actually, made a mind to start at 4. I did not have much idea that I have committed from 4:20. So only Besharul was online. Uh, Everybody else knew that we'll start at 4:20. Anyway,
Yes, right.
today I also want to practice with this thing.
Thing,
I
sir.
hope it will work. Okay, draw. Oi. Oh no.
So class start.
Yes.
Class started.
Okay. Maybe I need more practice on this. It's not very accurate. So stop share. Okay. So I think most of you are here. Khalid, Kainat, Ghafoor, Saif, Irfan, Besharul. Others will join as we move along. Uh, I'm sharing my screen. I hope you can see my screen.
Yes, sir. Yes, sir.
Okay, okay. So today we have yet another very important, and exciting set of topics. Today we'll cover a neural machine translation. We'll discuss about attention, and then we'll discuss about transformer. To be very honest with you, I told you in my previous class that the reason why we were learning all these early and neural network model, it was to learn, attention and transformer, because these are really really big things. They have caused BERT and GPT-2. So if you want to understand BERT and GPT-2, they are nothing. They are just, a stack of transformer, uh, and transformer is actually an extension to attention. So you will see that these developments have actually brought a lot of, newness in natural language processing. And they say when you saw attention and transformer, that was kind of imaginate movement in NLP, the way we had imaginate in image processing. This transformer and attention is having similar kind of importance in natural language processing. So most of the things that we are doing it with traditional LSTM and GRU, they actually took back seats because this transformer and attention, these guys actually made many things simpler. So today we'll see what actually attention is and what is transformer. But before understanding attention and transformer, we also need to understand neural machine translation, because neural machine translation is an area where transformer and attention has bigger impact. You will see that this neural machine translation is actually a kind of sequence to sequence problem, translating one sequence into another, maybe a sentence of English into Urdu, vice versa, a sentence of German in English, vice versa. Converting a question into answer is also a sequence to sequence translation. You have a question which is sent as a sequence at the input, and you want answer to that question. That is also sequence to sequence translation. So the sequence to sequence translation, or you can call it sequence to sequence modeling, that was heavily impacted by attention in transformer. So that is the reason why, in order to understand transformer and attention, usually you first understand neural machine translation. So, is there anyone in this class who has already covered transformer?
Yes, sir. Me.
No, no, sir.
I think I heard one yes. Who said yes?
Sir, Abdul Ghafur.
Oh, Ghafoor. Yes. So, what is transformer?
Sir, actually, problem was the uh, previous method like LSTM वगैरह. There is a to understand the contents. Sometimes we have the long text, so we have to remember the previous, because for example, word in the long text is the second index. It is connected to for example 12 index. Then we have to get this index, and another is a popular example. If words context, for example, bank also used to river bank, and bank also used to for the case, withdraw case. So how our model will understand where which word will be used. So these were the problems with previous methods. So these problems actually solved by the attention. So in the transformers, we only separate we in the transfer is just attention, but LSTM we have the attention and ornament. But in transfer is a simple attention, nothing else.
Okay. Any other opinion? Saif? Saif, I thought
And
you were covering it, Saif. Okay, maybe Saif might have gone to a break. Anyway, so thank you, Ghafoor. Thank you. I think more or less you have explained it. Let's see technically what a transformer is. What a you can switch off your microphone, Ghafoor. Okay, thank you, thank you. So this neural machine translation. Before understanding transformer and attention, let's understand neural machine translation. Neural machine translation is nothing, just conversion of one sequence into another sequence. So say for example, this is the sequence. We will have a model which will convert it into another sequence, right? So say for example, this input of circles have been converted into output of triangle, right? In neural machine translation, we usually deal with the natural language translation. So say for example, we have this in French. The sequence to sequence model will convert it into its corresponding English. You can see here, I am a student. So this sequence, which was previously in French, it has been converted in English, right? So sequence to sequence translation is nothing, just converting source sequence into some other sequence, right? Now that source sequence can be a sentence in one language, and destination can be a sentence into another language. This is simplest sequence to sequence modeling. But usually when you are dealing with chatbot, you can have input sequence as a question, and your output sequence is answer to that question. So when they write at the input, what is the deadline of applying admission at Sakurai Bay University Master's Program, this can be an input sequence, and output can be the last date to apply for Sakurai BA admission is December 15th, say for example. So you know that the input sequence can be in one language and output sequence can be another language, machine translation. In its simplest form, we can have, at source and destination same language, but source is a question and destination is an answer, right? So I mean, you just see around, there are many sequence to sequence problem, a lot of problems which require us to map one sequence to other. Those can be those can be done by using the sequence to sequence modeling, by using neural machine, right? So believe me, the sequence to sequence modeling, when you kind of unveil it, inside there is nothing, just an encoder and decoder. So encoder will encode this sequence in one format, and decoder will get that encoded sequence, and from that encoded sequence, decoder will be able to recover another sequence, right? So when you actually go in depth of sequence to sequence model, they are nothing, just a combination of encoder and decoder, right? Now remember how they actually work. The encoder actually takes a sequence and converts it into a context vector. We need to understand that sequence is nothing, just a vector, right? So what the encoder does, it actually converts that vector into a context vector. The decoder will take that context vector and translate it into, destination sequence. So what is context vector? I mean, how it is calculated, I mean, depends what problem you are going to solve, right? So say for example, if I have got this sentence in French, if you want to translate it into English, first you need to convert this into a context vector, right? So we will have a context vector here, then decoder will translate it. The decoder will translate it. You can see I am a student, it has been converted. So the whole thing that we need to understand, it is to see how a context vector is created from source sequence by encoder, and how destination sentence is created from the context vector by the decoder, right? I mean, earlier, before the advent of attention model, these encoders and decoders were nothing. They were just a recurrent neural network. They were just a recurrent neural network, RNN. I mean, they were LSTMs, they were GRU, multiple variants of LSTM and GRU, but mainly this encoder and decoder was nothing, just these RNNs. So this context vector is a vector of loads. I mean, nothing else. Usually 256, 512, or 1024 size. These are just word embedding. These are just word embedding, right? They are estimated through some mechanism. We'll see what that mechanism is. But actually, these are nothing. You just convert one word embedding into another word embedding. And that word embedding can be used by decoder to recover the destination vector, to recover the destination sequence, right? So say for example, if we have got this input in French, this first word might have this sequence. Say for example, if you are using, say for example, fast text. Now when you use fast text, you know that for each of the word, you can have a sequence, right? You can have a word embedding. So you can have a vector. So if you are using fast text, so suppose inside fast text, you have this word represented by this vector, another word represented by this vector, another word represented by this vector. Then the first step is to use one of these word embedding. Now when word embedding has been done, then you know that your encoder is actually an RNN. Your encoder is nothing, just an RNN. And just revisit of RNN. If you remember, in RNN, we say that we will be giving current input as well as hidden state, right? That hidden state is actually previous output, right? I mean, this way, RNN considers not only current input, but it also considers the previous state, and previous state is actually the previous input, right? And because previous input might have seen the previous input, that is the reason why RNN was considered very good at capturing the context, right? Based on current input and hidden state, we calculate the output, right? So at time stamp 1, an RNN takes hidden state and input vector, it processes, then it produces two output. The one is hidden state for the next step, and second is output for this stage, right? So we have already seen this RNN in our previous classes, so you should be able to understand how this process is being done. You know that H3 is actually function of H3 minus 1 and comma X3, where X3 is input and H3 minus 1 is the previous input, right? Previous output rather. So you can see here, if I say at time step 1, the encoder, which is actually an RNN, will receive a first input, right? The first word. From that first word, it will estimate first hidden state. At the second stage, it will take second input, the second word, and use, at second step. So this will be the input for time step 2, and also this one. So this is time step 1. At the time step 1, we actually have estimated hidden state 1, and this hidden state is actually output of when we send this at the input, right? So this is time step 1, this is time step 2. At time step 3, you know that there are two input. One is input this third word, as well as this will go at the hidden state as the previous state, right? So by using these three, we actually reach to hidden state 3. Now that hidden state 3 is actually your context vector. The hidden state 3 is actually your context vector. I mean, look at the beauty. You are using RNN and you are saying that when you have consumed all the words at the input, the state that you receive at output, which is actually the final output of RNN, you say that is actually the context vector. And decoder should be able to reproduce the corresponding English sentence from this context vector, right? So at time step 4, when you gave this context vector, from that context vector, decoder generated I, then it generated M, and then it generated F, and then it generated student, right? So in this way, you can see this encoder is nothing but an RNN, and this decoder is nothing but just an RNN. So to this RNN, we are providing context vector. From that context vector, it is actually producing the output sequence. And how that context vector is being estimated? It is being estimated by reading the complete sequence at the input. Let's see it one more time so that you can understand this concept. So the first step is you will have a sequence at input, which may be any which may be any sequence in French or in Urdu or in Sindhi, whatever your source language is. For each of the word in input sequence, you need to have embedding. Now this embedding you can learn by having maybe one hidden layer neural network, or maybe you can learn it by uh, loading pre-learned glove, or say for example fast text. I mean, whichever embedding technique you want to use, you just need for each of the word a number, a vector, right? So you can use pre-trained word embedding, or you can even learn your word embedding while training your sequence to sequence model, right? So here we say this word is being represented by this vector, this word is being represented by this vector, and this word is being represented by this vector, right? uh, so because each of these are actually RNN, so we need to quickly understand what an RNN is. If you can recall, RNN has got two input. One is the current input that we are sending, another is the previous state, right? Current input and previous state, both of them, RNN does some magic. You have seen that magic. That magic is actually an activation function. It can be 10H, it can be ReLU, whatever you are applying. But the output here, rather I should say the output state here is actually function on HT minus 1 and X3, right? then it produces the current state, and that also goes to the output, right? And then next time this output will be used as a next hidden state, and you will see the next input, and this process continues until you have consumed a full sequence, right? So here, if this is an RNN, we say that we will be sending one word at a time. So at time step one, we send one word, it produces hidden state one. Right? You remember when you are playing with RNN, it's up to you. Do you want output at each stage, or you just want output at the final stage? So here in sequence to sequence modeling in neural machine translation, we say that we will take output at the last stage when whole sequence has been consumed. So when you're doing sequence to sequence modeling, when you're doing neural machine translation, you might be considering one sentence at a time. So here this first sentence has been sent at the input, and we want to see what is its corresponding English. So one word at a time. So the first word we gave, it gave us hidden state one. Now at time step two, this hidden state one and second word, these two will be sent to the RNN. It will give us hidden state two. Then at time step three, we'll give hidden state two and this input to get hidden state three. Right? So hidden state three has been given. Now, when full sentence has been consumed, the next thing is you call this as a context vector, and this context vector is actually sent to the decoder, right? So this decoder will be able to translate, to recover the corresponding translation of this French in English from this context vector. So at time step 4, it will recover I, then am, then then student. I am a student. I mean, just don't worry. You might argue that, come on, here we see just 3 words. Jesus is student. I mean, this is French. Now, from this French sentence, you might argue, how come we are able to recover these 4 words? I mean, that is machine translation. I mean, this is machine learning. This is not dictionary. Yeah? This is not that you are mapping word to word. This is actually machine translation. So machine knows that when I say eat student in French, I need to produce a student. So this addition of a will actually be learned by the machine when you train it. And remember, this is not dictionary mapping, which means that we have trained this encoder decoder. We have provided sufficient data to this encoder to learn that when you see this sentence, the translation will be this one. Right? You will get more sense of it when you see it in example. Right. Now, let's see the unrolled view. You might not have understood it fully. So let's see it unrolled. So you can see here at first stage, you have an RNN, right? You give this as input. And from here, the initial input is coming. And that initial input is all zeros. That initial input is all zeros, right? So we provide 2 inputs. We get hidden state 1. Now, this hidden state 1 and this word, they both are sent to the RNN. It will produce hidden state 2, right? Then hidden state 2 and this third word, they are sent to encoder 3, which actually gives us a hidden state 3. Now this hidden state 3 is actually sent to the decoder, and which acts as a context vector, and then it will generate the corresponding English translation. So at time step 5, it gives you I, then am, then a student, right? So they are actually kind of recovering sequence from source to destination. Yes, Irfan, go ahead, ask question.
Sir, we, I understood what encoder is doing, but what decoder is doing? I mean, we are just providing it a context vector, which is actually hidden state 3, which has learned. But what will enable decoder to actually translate it?
The information which is in context vector 3, the information that we have in context vector 3, you can imagine this context
But see,
vector. This context vector is actually a translator. You can understand this guy sitting on the left is French, and this guy sitting on the right is an Englishman. The context vector is a translator, right? this context vector kind of represents French in some intermediate language, and that intermediate language is understood by the decoder. So when this context vector is given to decoder, decoder will be able to, completely recover a sentence from the context vector. Right? You might argue that, oh, how come? I mean, just one vector and a lot of information. So my answer would be that one vector is actually representing, when you closely see, you can see hidden state 1, hidden state 2, hidden state 3. Now you know that hidden state 3 has information of hidden state 2. Huh? And hidden
Right.
state 2 has information of hidden state 1. And hidden state 1 has information of, hidden state 0. So that is the reason why, end of the day, when you send this context vector, you are actually not sending only one vector, you are actually sending whole representation of the input sequence. So from that input sequence, this decoder is able to, recover the corresponding English translation. Got the idea, Irfan?
Yes, sir.
You will see, I mean, when practically we see it, you will make more sense of it. I understand it is difficult, it is hard to believe that how come just one vector and we are getting, complete, output. Huh?
Sir,
Now,
I'm just wondering that how the decoder is trained actually.
yeah, we'll see it. We'll see it. Don't worry. Yeah? Mm, now, let's pay attention. Now, attention
Right.
allows the model to focus on relevant parts of the input sequence as needed. I mean, at this stage, when we are at time step 7, this attention decoder, when it is attention decoder, it is actually to generate not only a student, but also a. It is able to generate, both values from here. Now, how it is actually able to do it, we'll see when we are doing it practically. Yeah. An attention model. Now remember, this is simple, neural machine translation, and it was there for ages. I mean, uh, as until 2014, this was the only model we were using for translation. But then in 2014 came the paper. The attention is what all needed. In attention, they actually says the encoder passes a lot more data to the decoder. Instead of passing the last hidden state of encoding stage, the encoder passes all hidden state to the decoder. I mean, that's the only difference. That is the only difference. I mean, this guy who wrote this paper, he actually became a celebrity in NLP, but his concept was very simple. He said, why you are sending only context vector, the final thing? Why do not you send everything? So he said, encoder, when you calculate all three states, send all these three states to the decoder side. Then decoder will be doing better translation. We'll see that. We'll see that how this is happening. I mean, an attention decoder does an extra step before actually producing output. It does not only say that send these three, state, but it also says at what stage you should focus on which context vector. It is not only sending blindly all these three, but it is also telling you that what you need to focus upon uh, in the input when you are doing translation. So this attention mechanism which they introduced is actually phenomenal. I mean, had he just given a recommendation to send all three, it would have not mattered, because the information that these three states are representing, more or less, just third state is also representing. But what this guy said, he said, send all the information to the decoder, but also do a kind of weighting mechanism. You need to assign weight to each of these context vector. And these context vector at the decoder side, decoder should know which of these vectors I need to pay more attention to when I'm translating. So maybe when he's trying to produce I, the attention mechanism will tell that focus on hidden state 1. And when I'm trying to produce M, it will tell the focus on hidden vector 2. And when we reach to 3 and 4, it will say that focus on hidden state 3. Now, how this weighting mechanism is done? I mean, the whole, gist of the paper is in that attention mechanism. So the attention mechanism actually determines, it actually guides the decoder to focus one context vector at a time. And how that focus is done? By assigning different weights to all these hidden states. So at any given time, at time step 1, we will have some mechanism which will tell us that focus here. At hidden state 2, it will tell us that focus here. At hidden state 3 and 4, it will tell us that focus here. Right? So we'll see that how that attention mechanism is made. So in order to focus on the parts of the input that are relevant to this decoding time step, the decoder does following. Look at the set of encoder hidden state it receives. Each encoder hidden state is most associated with a certain word in the input sentence. Give each hidden state a score, a weight, right? And then multiply each hidden state by software so that we can get kind of probability score. So we understand that where we need to focus and what we need to ignore. They say that the words which you need to focus upon, you will have to amplify, and the words that you do not need to focus upon, you kind of drown them. You kind of, at this stage, blur them because you don't need to pay attention to those. Wow. I mean, this idea actually came originally from image processing. You just watch this, you just watch this image. This image will give you an idea. Guys, if I'm when you saw this photo, what was the first thing that you paid attention to?
It's
Saif?
raining.
Saif?
It's raining, sir.
Saif?
Yeah, sir, it's raining.
Come on. Why you are being so, shy? I know that.
They are trying to be Sharif.
What is the most attentive thing in this image?
Sir, a woman is running. A woman is running inside the room
It's not a
or
woman.
inside the building.
It's a girl.
Inside the building.
Yeah, it's a girl. It's a girl.
It's a girl, sir. Girl, you can say a girl.
So they say that when you want to interpret an image, you very quickly pay attention to the most important content. And when you pay attention to most important content, everything else actually is blurred. You actually ignore everything else. For example, I'm saying, can you in this image figure out where is the ticket?
Ticket both or ticket?
Yeah, the word ticket.
The word ticket.
Yeah.
Yes, sir. It is here.
Sir, zoom the image. Zoom the image.
Sir, it's here.
Yeah.
Where it found?
Where the fat
tickets.
guy is standing.
Yeah.
Tickets.
It's the tickets. Tickets.
Yeah, tickets.
In white letters.
Right.
Yeah.
Okay. It means that when the query was find out ticket from this image, when you focused on tickets, you actually blurred everything else in this image. I mean, that is the human psychology. When you are asking someone that figure out where is the tickets booth, they will actually focus on that particular area, ignore everything else. So, human pay attention to the most important content, which are answer of the query. By default, when you saw this image, the default query was to just focus on what is most important, right? And the most important probably in this image is this girl who's running for many reasons. I mean, the reason can be because she
Depends upon individual, sir.
Yeah, it depends on individual, I know, but it is because she is the closest to the image. She is the most prominent in the image, and probably she is running. Usually when somebody runs, you watch at them. I mean, this is our nature. If we are sitting, if somebody is just passing by normal speed, we'll not focus. But if somebody is running with the 10 kilometer a minute speed, you will immediately pay attention to him. You pay attention because these are some of the rules that are embedded in our mind. We don't know how, but you usually pay attention to those who are running. Huh? You immediately you will be feeling very curious. Why is running? Probably it is because you are concerned of your own safety. He's running because he might have seen some murderer. He's running because he might have seen some bomber, right? So in that case, you pay attention to them because you are also concerned of your own security. Same is the case with us. I mean, everybody, whenever anybody is running, we pay attention to them. So the default query that we had in our mind when we saw this image, it was why she's running. When we saw she's running, then we figured out she's running because it was raining, right? And then when I changed the query, I said, where is ticket? So all of you actually focused on an image. At that time, probably you ignored this beautiful lady. At that time, you ignored that these two girls are also standing here. Huh? You ignored that these guys are probably taking a cup of coffee here. You also ignored what is written here. You just focused on this part. This is exactly what this attention guys in NLP are doing. They are saying that if you've got a big sentence and if you're translating word by word, you just focus on one word at a time and then see the context of it and perform a translation. So they say you need to introduce this attention mechanism that we generally have in image processing, that we already have installed in our mind. We just want to see how we can simulate this attention mechanism in NLP, right? So let's see how they actually do it. Let's see how they actually do it. So we get an idea, right? So we will have a yes question.
Sir, in a similar same image, you can say this: if you are looking for a text, then probably we'll be ignoring the humans and icons or anything, or the physical shapes or machine. As we are looking just for ticket written on somewhere, so we will just focusing on the text. But if you ask us to find ticket both, then we will probably be ignoring text and also humans, and we will looking for the buildings or shapes.
You're right. You're right. I mean, it depends on query. It depends on query. It depends on query. Whatever query you receive, you pay your full attention just to answer that query. This is exactly what attention mechanism is. Attention mechanism says you need to figure out at what time interval, what are the most important, context vectors, and then focus on those context vectors and produce the answer. So here, when we reach a time step 5, I mean time step 1, when we produce state 1, then state 2, state 3, at time step 4, when we were about to produce I, we needed a mechanism to focus on hidden state 1 and ignore 2 and 3. How we are doing it? See here, see the mathematics. I mean, mathematics will give you an idea. They say that at time step 4, when you've got all these 3 hidden state 1, 2 and 3, you know how they have been calculated. They say that for each of these hidden states, along with these context vector, you are doing a scoring mechanism. Don't worry where these 39 and 9 are coming from. We'll see where they are coming from. But you actually score each of these hidden state. You actually score each of these hidden state. So we say that hidden state 1 is given score 13, hidden state 2 is given score 9, and this is given score 9. Right? This is at the time step 4. When from these 3 hidden state, we want to produce I. We want to see how I is produced, right? So at that stage, decoder will also have a hidden state. Decoder will also have a hidden state because decoder is also an RNA. So decoder does not only have input coming from here. Decoder is not having only input coming from here, but it will also have input from here because this is also an RNA. This is also an RNA. So RNA will have not only the hidden state which is coming from the encoder side, but also its own input. So when you are training at the input, you will have the actual translation. At the input, you will have actual translation, right? But when you are testing, that input will be empty. That input will be empty. We'll see that. I mean, these are very interesting concepts. So we have H1, H2, H3. Somehow we generated these scores. We softmax them, these scores, right? And then we multiply each of these softmax scores to these vectors, right? So these vectors have been produced because we have multiplied, these softmax score to these states. So definitely the one which needs to be amplified, it is getting better weight. Because it is getting better weight, so it might have higher values, and because these have higher values, so this actually becomes prominent. At that stage, what you actually do, you sum all these three, and then context vector for decoder time step 4 is actually sum of all these three. Is actually sum of all these three. And then these are just a step you need to follow. The attention decoder RNN takes in the embedding end token and an initial decoder hidden state, right? The RNN processes its input, producing an output and a new hidden state H4. The output is discarded because we do not need at this stage. Attention state, we use encoder, hidden state, and H4, which we have calculated here. How H4 is calculated? By all this calculation, right? So we say that attention state is we use encoder hidden state, which has been sent, and H4 vector to calculate context vector 4 for this time step. We concatenate H4 and C4 into one vector, and we pass this vector through feed forward neural network, one trained jointly with the model, and the output of the feed forward neural network indicates output word of this time step, and then we repeat this for all other steps. So you can see here, now I think this will make more sense. So we received H1, H2, H3, right? At this stage, attention 4, we performed the calculation you have seen, right? The calculation we saw in the previous slide. Here at the encoder, we are passing first input and initial state, right? Both of initial state is all zeros. Initially it is all zeros, right? Both of them when sent to the, remember, when you are at the decoder stage 1, you are sending one encoding for the token end, right? So token end, that actually shows that input sequence has been ended. So token end embedding as well as initial state, which is all zeros, they both are sent to the RNN, and here we calculate hidden state 4, which is actually mixture of initial state and end token, and the C4 is concatenated here, and both of them, when they are concatenated through feed forward neural network, maybe one hidden layer dense neural network, through this we will have a weight matrix, and it has to generate I, right? Then H4 is sent here. This acts as a hidden state to the next stage decoder. The input will be provided from here, right? Again, this time, the C5 is estimated in the same way as C4 was estimated by this calculation, right? And then this C5 is concatenated with H5, and H5 is actually output of RNN from the current input and H4, right? H4 is actually coming from here. Both of them are concatenated through feed forward neural network. They actually predict M, and then this process continues, right? Now you need to understand one thing, which is very important. When you are training the model, here at the decoder side, you will have actual inputs. They are actually telling you, when you see this context vector and when you see this token, we have to generate I. right? And then we come here. We say that when you see the previous state, this previous output I, current input is, say for example here I, what should be the next word printed? Next word should be M. Right. Now, when you have already printed I and M, you come here at this hidden state. We say that when you see H5 and when you see at input IM, the input is M, because here we are kind of sending the actual data to the decoder side with one time step delay. So we are not sending, I am a student here immediately. We are sending end and then I am a student, right? So we say that when we see end and initial state here and this context vector, we should produce I, right? Now if you are unable to produce I, then you will do back propagation, the learning of the network, right? But if you produce I, then you come to the next stage. You say that here when you have got this hidden state and when your input is I, you should produce M. Next step, you say if this is the hidden state and if input is I mean input is M, then you should produce A, and so on. Right? At each stage, because this guy, the context vector which is being produced, they are being produced by some scoring mechanism. That is the reason why initially we are focusing on first, then we are focusing on second vector, and at the third stage we'll be focusing on third vector. So this actually says when you are here, focus on this. Rather than focusing on all three, focus on first. When you are here, focus on second. When you are here, focus on third. Right? We'll see that how this focus is actually estimated. We'll see that how this scoring mechanism is actually calculated. But when you see, I mean, these guys, they have got some weight matrix. They have got some weight matrix. We say that when we are training the model, we say that when you see end and context vector 4, produce I. Now, if network is unable to produce I, you say update your weights. Now, which weights you are going to update? The weights which are here as well as the weights which are in the encoder. So you will update the weights until you produce I. So you will be kind of, again doing back propagation so that you give understanding to the model that please produce I when you see these context vector and when you see this word at the input, which is initially end, right? So here we say when you have seen I and M, what is the next that you need to predict? In this case it is A. And then we say when you have got I, M, A and this hidden state, what you need to produce? It is a student. So you say that when you are training, you will have all these inputs available here. But during the test time, all of them will be empty. You need to just produce output from these hidden states. Right? So you can see here, when these were the three words, this is because of hidden state 1. So we say focus on this, make everything else blur. We have to blur everything else. Focus on 2, blur everything else. Focus on 3, blur everything else. Right. So you can see here, this attention mechanism is nothing, just to focus on the right hidden state, which is coming from the encoder. It says that ignore everything else, just focus on what is important at this time state. Right. Now, you need to understand how that focus is estimated. You have to be with me. In order to understand this concept, you have to be with me. In order to understand this mathematics, you have to be with me. This is a beautiful concept. Believe me, I mean, wonderful. Because of, the simple mathematics, they are able to, improve performance of this translation. They are able to improve, performance of sequence to sequence modeling. You can see here in the attention model, encoder, it is producing hidden state, sending to the next encoder. Not only that, but at the same time, it is sending its output to the corresponding hidden state in the decoder. Why we are doing it? We want that both these encoder and decoder should learn simultaneously. Both of them should learn simultaneously. See here, see here. This should make more concept. This should make more sense. See here, I'm saying that this was the input, right? And just make an assumption that you have, when you are doing sequence to sequence translation, at the translation time, you're not only giving the French words, but you are also providing the English words, right? So you say that, for example, through some magic, you have reached here, right? A time step, say, for example, this is hidden state 3. Now, what is the point? The point is we want decoder, because it is training. So what should be predicted here? It's already available here. It's already available here because we are training. We've already provided a sequence during the training time that when you see this French sentence, you have to produce this English sentence, right? Now, because we are training, so we are providing this at the input. But when you are at the during the test time, this will not be provided here because at the test time, this input will not be available, right? So what we are saying that this word that you need to generate, it will be generated by context vector 3. What is context vector 3? Context vector 3 is actually mixture of all these states, all these words at the encoder side. So when you gave LE, hidden state 1, you send to the next encoder, but also send it here. When you send this word, you got hidden state 2, you give to the next encoder, but also give that here, right? And continuously giving all these values here, and we actually say Eij equal to, look at what is context vector I. So this is context vector 3. So what is context vector I? The context vector I is actually some function, some activation between I and J and all previous states This is sum of all these three, sum of all this product, right? Where this alpha is nothing just softmax, and this is softmax between what? Softmax between some 10H or maybe ReLU between previous state and current input. Previous state and current input, previous state and current input, previous state and current input, right? So we say that this Eij is actually previous state and current input, previous state and current input. You get all these three, estimate softmax and do that summation. So the C3 is nothing, just sum of all these multiplications, sum of all these multiplications. And the good thing is, it is not only that you are considering encoder side, but at that time you are also considering the current hidden state of the decoder. So you say Si minus 1. So you want to predict fourth word, so you focus on what you have predicted at previous state. So whatever you have predicted as the previous step, that thing and this whole sum, right? These both are being sent to the decoder. Now you can see a lot of information is being supplied. We say that, now say for example, at this stage, we do wrong prediction. So they say they do back propagation. So initially maybe the hidden state here might have weights which are giving more preference to H2. But when we saw wrong prediction, we'll say change your weights. We do not need your contribution. So what we will do, we will actually pacify the contribution of hidden state 2, pacify the contribution of hidden state 1, pacify the contribution of hidden state 3, and amplify the contribution of hidden state 4, that is actually called the attention, because you are kind of getting input from all, but when you got input from all, you saw the error. Now when you saw the error, you do back propagation, and when you do back propagation, you do nothing, you just update weights of all these, because these are RNN, so they must have weight matrices, so you will be updating these weight matrices. So if with the random weight matrices, the contribution from H1 and H2 and H3 was higher, you will say, come on, you pacify. Because at this stage, we do not want to focus on you. If even these guys, 5, 6, 7, they were contributing more than anything else, at that stage, we'll say, come on, reduce your weight. We will just amplify H4. Because at that time, we know that we have to focus on this. We know that we have to focus on this. So that is the reason why we will say that, reduce your weights, increase your weights. So here, when I say we will have these scores are nothing. These are softmax scores. And where these softmax scores are coming from? These are actually, these softmax scores. They are coming from the learning. They are coming from the learning during the training time. So at the training time, we know that when I have seen, at the end, a hidden state, and the previous word is bird, I need to know what I need to predict. If that prediction is bird, then weights are okay. But if that is not bird, then I update weights of all these encoder. And when I update weights of all these encoder, so maybe I was doing wrong prediction. I was not predicting bird because H1 was having more contribution in this quantity. So I say you have to reduce your weight. Huh? And then I reduce weight of H2. I reduce weight of H5. I actually amplify H3 or H4, which is actually kind of input I need to be focusing on that stage. So, that concept of focusing on what is important at that stage is actually simulated in this by these simple formulas. So here, the attention mechanism says, do not consider encoder and decoder separately, rather both of them can learn simultaneously. So encoder is kind of having a good view of decoder, and decoder has got a good control on the encoder. So decoder can, update weights of encoder, and encoder can see what is happening in the decoder. Now, because they are collaborating very closely, so they know that what we need to do at each stage. So the important thing is we are learning these weights at the training time because we know the output, and then when we are in the test stage, this input will not be available. We will just be using these weight matrices to predict what should be the next word. This is the basic concept. Do you understand it? Any question up to this point? Yes, Irfan?
So this is what I was asking at that time, that how the decoder is trained actually to see what encoder has generated and I have to decode it. So this is the actually mechanism you just explained.
Right. So you are clear now, huh?
Yes, sir.
Okay. Nimra, you raised the hand, eh? Yes. Nimra, I can hardly hear you. Can you come closer to the mic?
Sir, can you hear me now?
Not really.
Oh, MG. Sir, let me just.
Sir, volume up, sir. Yes.
Sir, मैंने अब hand पे remove कर दिए.
Okay,
Sir,
absolutely.
I was just asking कि this context vector is basically the combination of all these words. So how it will be different for all stages? Means I'm not getting this concept actually, or completely.
See here, Nimra. See here. I mean, when we start, if you just understand this picture, you will understand whole attention model. What we are actually doing, first of all, we send this to the input, and because this is RNN, so RNN have two matrices. Huh? If I can quickly show you RNN, If I quickly show you
Yes, sir.
the RNN, you need to have a good grip on RNN in order to understand, this one. So if you see what RNN is doing, this is RNN. If you see this example, I think we saw this example.
Yes, sir.
RNN, you have input, right? At input, you have got, input matrix and X tree. And, at the out, and when you also get another input which is coming from the previous state. So
Yes,
the
sir.
input which is coming from here is actually H3 minus 1 and another, hidden layer matrix. So these two matrices, this matrix and this matrix, they will be getting random values initially. They will be getting random values initially. Right. Now, if you see here, when you gave LE, we gave here, and initial state is all 0. Right. You get H1. You get H1. But when you got H1 at that time, you have already initialized WHH and WXH. Right. So that WHH and WXH, they have been initially randomly initialized because this is a neural network. So they will get initially random values. Right. Now we get this hidden state, we keep it here. Say for example, we keep it here. For the time being, just imagine we are not processing output. We are not processing output. So when we got this input, we give this state to the next encoder. When next encoder comes here, it gets this input. Not only this input, previous state, the previous state is being multiplied by WHH and input is being multiplied by WXH, the two matrices. Right. Now with these, it will produce H3. I mean H2. Now H2, for the time being, you just understand we are not processing. This output is there. Only H2 is being sent to the next encoder. When we saw this input, this is the input, and we have got H2 coming here. We produce H3, and we not only produce H3, but we also have two more matrices, WHH and WXH. Right. So same way, we actually continue till we reach here. Until we reach here. Now, when we reach here, that can be considered as a, say for example, S0. You can call S0. The output which is coming from here, you can consider S0. We say that when you give S0 and when you've got nothing at the input, remember we are in the training phase. When you are in the training phase, what they say you delay the translated sequence by one vector. So why they say it? Because we want that network should do the prediction. So we are kind of hiding, input by one time step. So we say that, tell me what should be the next word. We are giving him nothing. We say, tell me what should be the next word. Right. Now, at the input, we are sending them the embedding for the start token. Right. So we have a start token embedding, and the output is coming from here, and we say the prediction should be there. Now at this stage, we are not only getting input from here and here, but we are also getting input from here. I mean this whole C0. This is stage, this is C3, but when we are producing there, at that stage it was C0. So C0 is also coming here. C0 is also coming here. Right. When this is coming here, if the prediction is there, we say that's correct. You don't need to do anything. But when you say prediction is incorrect, you actually come back, do back propagation, update all these weights. Now, when you are updating all these weights, it means that some of the weights are being minimized and some of the weights are being maximized. It is just that you're amplifying some input and kind of introducing noise into other inputs so that their contribution is minimal. The whole magic is in this equation. C3, how you calculate context vector. We are calculating context vector by, sum of this product. And what is this, H3? H3 is the previous state in the decoder. And what is alpha ij? Alpha ij is actually, sorry, hj is the previous, the state in the encoder, and is I minus 1 is the state at the decoder, right? So alpha ij is nothing, just softmax between hj, right, which is current state, and a previous output at the decoder, right? And current state is not only one, these are all, right? So when you are here, you are not only considering the current input, but you are considering all of them. You are considering all of them. So you say that I'm giving you three information. The first information is input is a start. The second information is the context vector coming from decoder. The third information is I'm giving you this whole thing. I'm giving you this whole thing. What you need to do, we say to the decoder that you have to predict that. So say for example, if luckily it produces that, we say good, very good. We then come here, and that output is actually S1. Now this S1 is telling that what is the previous output? The previous output is that. The next step is we say, if this is the previous output, and I'm giving you this whole equation here, right? And if the input is there, what should be at the output? So it's kind of doing next word prediction. So we say that if the input is there, and if this is the output from the previous decoder, and this whole equation is also coming here, you have to predict little. Now if you predict little, will be okay. But if you do not predict little, we say you need to update the weights. And there are a lot of weights, lot of weights are here. So we say update them all so that you are able to produce little, right? And then we come here. We say if you have got this hidden state at the input, and this whole calculation is here, and input is little, tell us what should be next word. If you produce word, we say good. If not, then we say update your weights, right? So you know that when you are training the model, at each step you are just predicting one word at a time. And when you are testing, this input will not be there. This input will not be there, right? At that stage, you will only have previous state coming from here, and another input is coming from here. Because this is RNN, so it needs two input. So at least two input. So the second input we are getting from here. The second input we are getting from here, right? And then because it might have seen enough data, so it should be able to reproduce the corresponding sequence, which is your target sequence, right? Get the idea?
Yes, sir. Thank you.
Yes,
sir. Yes, sir. Thank you.
I mean, you just need, when you are seeing this on the paper, you should visualize in your mind what is happening at each time step. And internally, when I'm saying that you will have to increase weight of some state and decrease importance of other, by that I mean that you are actually updating weights in that direction. You're updating weights in that direction. And you know that when you're doing neural network, error will actually guide us how to improve. Our mistakes will actually guide us how to improve. So these weights will be increasing because we have got very efficient backpropagation algorithms, right? Got the idea?
Yes, sir.
Okay, good. Okay, so we'll see this later on. You got this idea, you got this idea, you got this idea. I think now you should be clear. I hope that when you study it, read it, you should be more clear on that. I request all of you. These are 3-4, tutorials that I want you to study. These are 3-4 tutorials, not one. You will need to read many. Attention and transformer. These are 3 tutorials which you need to cover. There are many. I have read at least 20-25 different articles and tutorials to develop my understanding, but I have reached to the conclusion that these three are probably the best. So you need to read all these three to make more sense of whole attention model and transformer, whole attention model and transformer.
Sir,
Right.
please share these links in chat.
I don't know where. Okay, yeah, decoder, attention, and then this one. So this
or in group maybe.
Chat. I'm sharing it on chat, right, to everyone. Okay, so this is attention. This one is transformer. This one is transformer, right? And this one is also transformer, but with better examples. There are many. I'm not saying read all, but these three I found best. These three, when I read, this is also giving you implementation in PyTorch. So if you're interested, you can do that. But they will give you a good foundation in understanding mathematics behind transformer and attention. Attention, EPUB, okay, transformer photo zoom, transformer tutorial. Yeah, this one is fourth one, which is also an excellent tutorial. Majority of my presentation that I'm delivering today is based on this. So you should also read this tutorial. So these 4 tutorials, and you should be able to grab the whole concept of attention and transformer. This also explains brilliantly. This explains very brilliantly. You can see this decoder thing. And then transformer, I'm coming after break. I think it's namaz time. So after namaz, we will see implementation of neural machine, and then we'll continue from there. So you can have a break of 10 minutes.
No sir, 20 minutes.
20 minutes.
सर वो हम नहीं मौलवी जो पढ़ेंगे ना हमें तो पीछे खड़ा होना है.
Okay. So what I'm going to do, I'm going to stop this here so that I can save it and upload on the LMS. And when you come back, I will be rejoining at 5:50. At 5:50.
Right. Thank you, sir.
Thank
you.
Sir?
जी सर.
सर ये एक्चुअली आज हमारी ये लास्ट के 15 मिनट्स में मीटिंग है ना उसकी प्रोग्रेस की. हाँ. तो मैं उस टाइम शायद ट्रांजिट में हूँ क्योंकि मैं आईबीएम में हूँ, तो 7 बजे बस जाती है, तो मैं रास्ते से ही मीटिंग में कनेक्ट हो जाऊंगी.
सर क्लास कब तक चलेगी सर? तो उस हिसाब से फिर हम कर लेते हैं. क्लास मैक्सिमम कब तक चलेगी?
7
तक. सही है. ठीक है. ठीक है सर.